Hello, welcome to the latest episode of Data Unchained. I'm your host, Molly Presley. Before I introduce today's guest, let me tell you a little bit about what Data Unchained covers in our conversations. We really focus on the changes that have happened in the world related to decentralized data, as data has started to be created everywhere, from sensors across clouds to devices, even in space. The access to data sets has become increasingly challenging because they're distributed, and yet the hunger of enterprises, research institutes to have access to data for their AI training, for their data analytics initiatives has become increasingly strategic. Data Unchained digs into some of the challenges with decentralized data, as well as the solutions that are emerging to really help in this area. And then ultimately, what are some of the benefits your organization can get as you tackle these challenges? Today's guest is a familiar face to those of you who follow our show. David Flynn is the founder and CEO of Hammerspace. David, welcome.
Thanks, Molly. Glad to be here.
Today's show, we're going to dig into a new initiative that Hammerspace is a part of called the Open Flash Platform Initiative. Maybe you can just talk a little bit about what is Hammerspace's tie to this initiative, and maybe give just a little bit of a summary of what is an Open Flash platform.
We are one of many participants on the Open Flash platform. I'd like to think we have a critical role in the fact that it does require a standards-based parallel file system architecture to truly benefit from the Open Flash platform architecture of distributed flash, without a lot of computing horsepower to dilute its capacity density and power density. So Hammerspace brings to the table the infrastructure for data orchestration, single global namespace, parallel file system. All of these things are incredibly important when you're working with a sea of networked flash, which is the OFP.
Data Unchained, I just emphasized it in the intro, is about decentralized data. The Open Flash platform is accomplishing a pretty massive record as far as being able to put an exabyte in a rack. Kind of how do you reconcile the two of now? We're talking about architectures that can fit massive amounts of data in a fairly compressed space. And, is the data going to all be created there, or how does it get there? How do those two come together?
Well, I think this goes to some of the challenges with the AI world, in the fact that GPUs are very power hungry, and you can only put a finite amount of them in any given location because there's only so much power available. So we end up with neoclouds being much more geographically dispersed than the traditional monolithic public clouds. So it starts with that, and then you get to the fact that for these AI workflows to be effective, all of the data needs to be local. So you end up having to house data sets in each of those facilities, and potentially redundant data sets there. So that's, compounding factor number 2, geographic dispersion, needing data sets local to each. And then number 3, with Gen AI, we are generating, massive amounts of data with these AI tools themselves. And that's, compounding on the fact that now we need to get them large amounts of data. So the Internet of Things and having everything instrumented to provide data suddenly has become really valuable because you can make sense out of it. So we're not generating more data at the edge. We're needing to put that at each one of these facilities. It's generating massive amounts of data. So really all of this comes down to the fact that we are now in the era where the exabyte is the new petabyte. Petabyte used to be this humongous thing, 1,000 terabytes, right? It was kind of this unattainable thing. Now petabytes are trivial. Tens of petabytes are trivial. Hundreds of petabytes are very common. We're talking now about people having increments of exabytes at these facilities.
All right, David. So let's put this in a little bit of perspective. I think, Tom Cruise is pretty well known in several of his movies about talking about really futuristic concepts. And you drew, at least to my first attention, that he was talking about in one of his latest movies, this kind of big concept of an exabyte in a data center. But we're talking about an exabyte in a rack here.
That's right. Yeah, it's his new Mission Impossible, the second half. He talks about how the AI wanted to get access to this data center because it was huge, and it was also hardened against nuclear bombs that it wanted to let off. But, it was an exabyte of capacity. And we're saying, that fits in a single rack now. It's like Hollywood's a little behind.
And this isn't an impossible mission. This is quite possible on the forefront of what this initiative is working on.
Humans have a hard time conceptualizing geometric growth and, storage capacity and the amount of data that is being generated now is one of these exponential growth things. So exabyte is the new petabyte. Petabyte's the new terabyte. And all things have to adapt. Being able to fit that much data in a single rack with a reasonable amount of power is just incredible. To put that in perspective, doing that with tape, even robotic tape system, which we think of as some of the highest density stuff out there, that's 30 racks, 30. And if you wanted to do that with, say, a flash platform, even the highest density SSDs available, with something like VAST or Pure, you're talking about 20 racks worth of gear that can fit now in one. And the complexity, the power consumption, all of those things are commensurately reduced. It's not just about the space. As a matter of fact, it's less about the space. Data center space isn't nearly as constrained as the amount of power. And by eliminating the server entirely, we can completely reduce the power. So that's one of the top benefits. We use space as a way to visualize it because humans are very spatial, but it's actually the power density. And you're talking about, mere watts per petabyte. That's just crazy.
Let's talk a little bit about power. We do hear there's a lot of news articles out there and intentions from the big AI companies, OpenAI, some of Elon Musk's companies, to build new data centers specific for AI. And a lot of it has to do with power, heat, cooling management. How would Open Flash platform fit into some of these new types of data center designs?
Well, it's twofold, compounding. Number one, basically eliminating any measurable amount of wattage required for storing data frees up that wattage for holding GPUs. And the power budget in a data center, maybe 15 or 20% of it goes to the storage. That's even in a flash system and even in a capacity optimized flash system versus the GPUs. But with something like OFP, reducing that by another factor of 10x, you're talking about the storage taking sub 1%, 2%, freeing up basically everything to be that for the GPUs. That's number one. Number two, OFP is inherently a parallel architecture where every single one of the sleds is an 800 gigabit and 4 petabyte unit. That means when you get to an exabyte, you have a couple hundred of these things and something that does 200 terabits a second, 20 terabytes per second of bandwidth, all of which can be delivered because there is no controller servers to front end this thing that constrain the throughput. So it's scalable linearly to those kinds of crazy numbers. And that what that means is that those GPUs are never having to wait for data sets. The ingest on the job start, the checkpointing while the job's running, the dumping of the data at the end, the fetching of pieces along the way. All of those things are nearly instantaneous when you have that kind of parallelism and performance.
I kind of think of it, there's kind of the trifecta of different issues that AI is creating for infrastructure and the enterprise. There's certainly access to data and the need for data. Power efficiency is a big concern, but spend too. How do we free up if we're not Elon Musk and have somewhat limitless access to money? Spend is a big deal too, and I think OFP has a really strong story there for both enterprises as well as the neo clouds.
That's right. Nobody has time to waste money to waste on the storage infrastructure. You want to put all of that to the compute, and OFP achieves a phenomenal improvement to TCO. Today, when you build a storage subsystem for shared storage, at least 30% of the bill of materials, 30% of the infrastructure cost, just the hardware cost, is going to the servers and networking and all of the stuff that's needed to build a storage system. With OFP, we eliminate the servers, the multiple layers of systems, the networking that's needed, thanks to parallel file system architecture. And we remove the server by going to nothing more than a network adapter and the flash. No need for a server at all. And because it's natively serving NFS files, standards-based, that's the foundation for the parallel file system. So there's no controller nodes needed out front. So it eliminates 30% of the CapEx from a hardware infrastructure perspective. Then, because all the servers are gone and all that internal networking is gone, you've reduced 90% of the power, which is your main thing, to OpEx, but equally space, cooling, and the servicing, because getting rid of all that componentry also means it's way more reliable. So on a per unit of capacity basis, you've just reduced every single dimension of OpEx by 90%. Now, OpEx is really relatively small compared to CapEx on a flash system, but fine, it still all adds up, especially when your power budget's capped like we were talking about. But the third and final thing is that by eliminating the need for servers and networking and that 30% of CapEx stuff that's now gone, the flash with a network adapter can easily be rated and supported for an 8-year life or even more. Whereas typically, as an industry, we end up throwing the baby out with the bathwater. We throw the flash out with the server and storage systems that it's bundled in, because those server systems, just like any server system, aren't really supportable beyond about a 5-year window. So it really is throwing baby out with the bathwater. The value's in the flash. It's still perfectly usable. The funny thing is when I first heard this from the team at Meta, they're the ones who brought this to my attention, because I hadn't really included that in my calculations on this. And they reminded me of the fact that the Fusion IO flash devices that they purchased from my previous company that I founded, Fusion IO, were so over-engineered that they lasted way longer than any of the servers they put it in. And because at that early period of, SSDs were quite expensive, so valuable, they actually took the time to crack open the servers, pull out the cards, put them into new servers, and give them a second life in a new set of servers. Now, nobody does that today. It would be a nightmare having to deal with the fallout and all of that. But, for them, they're at such a scale that the elbow grease was well worth it to extend the lifetime of those premium parts. But, this really drives home the point that lifetime matters when you think about it in terms of 5-year life versus 8-year life. That's 60% longer life. So if you look at it in terms of cost per petabyte per year, and you just extended that, it's massive. So 30% lower CapEx, 90% lower OpEx, 60% extended life. These things add up to an over 60% lower TCO, 63%. And what that means is that you're paying about a third. It costs a third of what the other stuff cost, just on a hardware basis. It's just astonishing. That means I can put in 3 times as much, right, for the same dollar. And so for the neoclouds, hyperscalers, and even enterprise America, this is how we get to where exabyte is feasible. Got to lower the cost. I mean, we were already flirting with flash being less expensive on a TCO basis than hard drives. But if I've just cut the cost of flash down to 1/3 of what it is, that means there's no question that you would go to an all-flash architecture, even for your deep retention tier.
So when you think about enterprise adoption, David, is this just the enterprises who are thinking exabyte scale capacity?
Or you mean just the hyperscalers? Because enterprises, I don't think...
An organization that has that kind of capacity in mind.
Well, while we talk about putting an exabyte in a rack, that's a way to really visualize just the full impact of what we're talking about. In reality, that's not how most will deploy it, except for the largest of these neo clouds or hyperscalers. Most would basically go the opposite direction. And the interesting thing is the architecture allows for that, and that's to go very granular. You would put a tray with the potential for 5 or 6 of these sleds that are, several petabytes each. You'd put a tray, it's just one rack unit of space, maybe right below your top of rack switch, where you generally have a few U of vacant space anyway. And you might put in 1 sled or 2. You might even put these into your rack spec, even though you don't foresee any storage needed at all. And it's completely empty because that tray is, largely just power distribution. There's nothing to it. There's no IP in it. The sleds hold all of the complexity. It's the DPU and the flash. That expansion capability in the granular unit of expansion, you just slide one in, plug in the network, and you've got more network storage. Slide another in, plug it in, slide another in, plug it in. So the elasticity of it, and because it's so high density, it's basically not occupying any measurable amount of space, power, cooling in the data center. Matter of fact, the most measurable thing is the network port that goes to it, which could be 100 gigabit, could be 200 gigabit, could be 400 gigabit, could be dual 400 gigabit to each one of these modules. That's how fast they go. So in that sense, you have the ability to have extreme scale down and scale up. And while I talk about these sleds being multi-petabytes, you could populate them with less dense NVMe and have something that's even more granular. The DPU, again, is so inexpensive compared to a whole server that even at much lower capacity points, it's still a very cost-effective way to aggregate. So talk about exabyte, but enterprise is probably going to use it for the very elastic nature of it and the granular nature of it.
So while they're starting to deploy OFP in these smaller increments, they'll still get the benefits of more power efficiency, the longer deployment life, all the things that we talked about earlier.
That's right.
They can still operate longer. They can.
It's kind of like the storage just disappears into the corner recesses of the data center, and it's no longer a resource consumer of any measure.
And I think particularly in the last couple of years, as GPU computing and AI have become such a front and center focus for organizations, does the performance density kind of track with the capacity density, or maybe talk a little bit about that as well?
Well, we are talking about all of this as the new capacity tier that just happens to get massive parallel file system scalability. The truth is the performance tier is also being transformed thanks to this native parallel file system that's in Linux. And that's our tier 0 technology, where you can aggregate the NVMe inside of your GPU or other compute nodes into making that shared storage. So the new performance tier is moving forward into the compute where it's even higher performance. And the capacity tier is eliminating the servers and shrinking, becoming much more cost effective, power effective at putting large quantities of flash in the data center. But if what you wanted is creating a high performance pool of shared storage, this is the best architecture for that. If you think about it, the next big supercomputer that Los Alamos is putting in needs to do 10 terabytes per second of bandwidth so they can checkpoint the memory across this massive supercomputer. At 10 terabytes a second, takes 1 second for every terabyte worth of memory that you need to dump to storage. And there are a lot of terabytes of memory. Or for every 10 terabytes, it takes a second. With traditional architecture, a I/O subsystem capable of that would have taken 5-10 racks of gear. With OFP, it's half a rack. It's just something like 20 trays. with 5 modules each. Very, very high performance density. So it just so happens to have the highest performance density of any shared storage out there. And yet we're positioning it for the capacity density aspect of it.
You've mentioned, a lot of the benefits and a little bit on the technology on how you accomplish it. And talking about pulling out servers, I mean, surely since everyone else has these servers that are controller nodes and keeping track of the data to the bits and how they're laid down on the devices, that's a necessary function. How can you just tear them out of an OFP device?
So those controller servers, they're adding the file system. And this fundamentally comes because flash devices are block storage. Somebody has to add the file system. And if you're going to build shared storage, it needs to be a shared file system. When it comes to building shared file systems, there's 2 architectures. You can use classic scale-out NAS, where you put a wall of controller servers that diffuse the data across your back-end storage servers, and you have to have this internal network. Isilon used InfiniBand for that internal network because it's what becomes the limiting scaling factor. You talk all to all. In the vast parlance, you have C nodes and D nodes. And the C nodes talk to the D nodes, and the C nodes are what are adding the file system and speak do the protocol to the ultimate clients. Even if you collocate the C node function on the D node, you still have to go into the box and out into all the other boxes. So you still end up having the same number of network hops. It's just now you've folded it in on the same servers and they're doing double duty. It doesn't help to collocate the C node and the D node. But all of this means you have a massive amount of compute horsepower needed to do all of this. What makes OFP and parallel NFS so unique is that the data can originate from the node as file system, a local file system with local NFS. Because with data orchestration and parallel NFS, you can aggregate those in mass to form a single logical namespace without the need of a controller layer. It puts the control plane to the side, a sideband control plane. Removing that wall of servers out front is what removes 90% of the power. That and the networking and the other layer of service, once you get rid of all of that, 90% of the power is gone. 90% of the space consumption's gone. It really is an architectural marvel to be able to do everything that's necessary to create a massive shared storage environment from a sideband controller that's not in a data path. That's been used in the supercomputing world with exotic file systems for a long time. It is now standard and built into NFS and Linux. And that's what makes OFP possible, is that now Linux contains the entire data path from the storage node up. And that means that in OFP, all you need is a NIC that's a DPU running Linux internally, and it can serve file natively. You don't have to add another layer of boxes out front to add the file system. Very long answer.
Okay, so you have a DPU running Linux managing the data path, and then out of band, there are some of the file system smarts. And that out of band bit, is it the same number of servers that a scale out NAS company would have, or is that consolidated down as well?
No. That's just the metadata service. It's a handful of servers, and it doesn't have to scale with your data throughput. And your data throughput is no longer constrained. That's why parallel file systems get perfectly linear scalability. And scale out NAS, after a few dozen nodes, you're not getting more performance. You're just making your performance worse. So it's a dramatic difference. Now, let me point out, one of the key innovations to have this work is actually improvements to NFS in Linux to serve data more optimally. We are pushing upstream in Linux today with the help of Oracle's Chuck Lever, who's the kernel maintainer of the NFS server stack, and our CTO, Tron Mikkelbus, who's the kernel maintainer of the NFS client stack. We have enhanced the kernel to be able to serve NFS, zero copy, no CPU touches at all. The data can come off of NVMe through a file system like XFS and out the network without the CPU having to wade through the data even once. The DMA engines can put the data into the NIC without it having to go even off the memory bus. This means, and just to put this in perspective for those who may know the space, just like NVMe over Fabrics allows a remote block access protocol that's very efficient, so you don't need a heavy amount of processing horsepower to put that data on the wire. This lets you do the same thing, same efficiency of NVMe OF, but at an NFS and file system level. That's the game changer there, and is what allows you to build a parallel file system with no controller nodes and no heavyweight servers anywhere in the data path.
So you're touching on this, and for some folks who maybe aren't as close to some of these technologies you're talking about, I think it would be good to kind of summarize. For most people, we think of, you mentioned tape systems, or when you think about really high capacity, high density storage systems, typically that's been thought of as archive, like the cold storage that's put tier 3, tier 4 or somewhere. Is that the trade-off that is happening with OFP, or can you still use all this data in a high-performance way for connecting to GPUs?
That's the amazing thing, and it really goes along with one of the other demands of the AI world. No data is ever allowed to truly be cold or even warm. Everything ultimately needs to be hot. You need to be able to wade through any part of that exabyte of data very fast. And this architecture really is putting everything into an ultra-high performance tier 1, but with all of the efficiencies that you would expect from tier 2 or tier 3, even more so because you've gotten rid of so much of the trappings that other architectures require to turn that into shared file. POSIX file.
So when we think about Hammerspace's role in OFP, maybe you can summarize what's the motivation for Hammerspace? What are we contributing to the initiative at Hammerspace?
Hammerspace is really at the forefront of the parallel NFS revolution. Having a parallel file system that's now native to Linux is a new thing, and we are the ones that have made that happen. Having a parallel file system that's native to Linux, where the data path is nothing but off-the-shelf Linux. The control plane is where all the complexity and proprietary IP is. But because of that, it allows us to move the architecture in this direction, elimination of multiple layers of servers and fat CPU and a lot of proprietary IP. So you could say Hammerspace is the catalyst that's making this possible. But there are other mega trends that are complementary. For example, move to ARM or RISC more generally in the data center and embedding in the network adapter a miniature server made with RISC processors. The elimination of big heavy x86 servers, the consolidation to a server on a chip combined with the NIC and the server processors. So we are seeing the revolution in the data center as we move to ARM. And that revolution is best achieved when it's compounded with the consolidation of the network adapter in with it and shrinking the server down to a chip instead of a bunch of stuff. Maybe you have external memory modules, but just a chip and memory, and it is the network adapter, and then put NVMe off of it. So DPUs shouldn't be thought of as smart NICs, or they should be thought of the next evolution of the server in the data center to a single system on a chip. And but it does have less horsepower, and with this parallel NFS being native Linux and built in, it allows us to fit. So Hammerspace can use this because the fixes we've done to NFS to be able to be served so optimally that you don't need any significant amount of horsepower there in it.
So this is the convergence of a lot of innovation from SSDs to DPUs to smart NICs, file systems. When do you foresee all of this coming together and being available as a solution in the market?
So we are going to be providing units to customers before the end of this year in Q4. And it really is remarkable. I will point out two other things. Number one, Moore's law and the fact that we're able to miniaturize more and more on a chip because we get so many more transistors. That's one of the reasons why we're able to build a server on a single chip. That and the move to RISC-based instead of the power-hungry x86. There's another key innovation to OFP that shouldn't be glossed over. It is one of the reasons you can get so much higher density. It's not only the elimination of the server and replacing it with a miniaturized server on a chip that is the DPU, but it's also the realization that once you get rid of the servers, now the flash doesn't need to be hot swappable because it's not like it's occupying a slot in a premium machine. Instead, you can allow the flash to degrade in place, maybe even have whole devices fail, and there's really no opportunity cost for not swapping it out, especially if you have encryption and you can ensure that that data that was on it is erased merely by forgetting the keys. Then you can allow these devices to fail, and with the parallel file system and distributed data, it just means you have a minor reduction in capacity over time. There's no reason to go in and service anything. Now, why does this matter? Because hot swap costs us much more than we think, and it was already a holdover from the disk drive era when you had a very cheap media, almost like tape. Disk is the new tape, right? And it was super cheap, and it was going into this expensive server. So if it failed, you wanted to replace it with something else, so it wasn't wasting the slot of this expensive system. So we built SSDs to follow that same model, even though they cost way more than the servers they plug into, and they're solid state. They have the potential to be, and actually generally are, much more reliable than the server they're plugging into. So why are we keeping this hot swappability? But now if we get rid of the server altogether and it's just a bunch of SSDs in the NIC, that can become your field replaceable unit, or just let it degrade in place and it reduces capacity of the overall system. And thanks to Hammerspace and orchestration, you can rebalance and repair, redistribute, resilver data, etc. So when you get rid of hot swap, you're no longer limited by the surface area of the faceplate, and you can put the flash deep into the rack, multiple rows of the flash devices. You can get rid of the hold-up capacitors. That's one of the reasons why SSD form factors are as big as they are. They have to have enough room to store power so that when you pull them, they can cleanly shut down. If it's embedded, you put hold-up capacitors in the entire OFP sled, and it holds up the entire system, network and all. That has its own benefits of now you can acknowledge writes when they're received over the network, because the DPU and the SSDs are held up together. But that takes the capacitance off of the SSD individually, so now they can be much more compact. You also don't need the mechanical rigidity that's necessary. You just need heat spreading. You don't need whole packaging. And you can put the connector on the long side where it's belly down, and put it, instead of putting it on the narrow side because of the faceplate space constraint. And that allows you to put it at the center to put a lot more flash in there and have a lot more usable flash with shorter signal traces. So there's just this compounding benefit when you make the transform to go, why are we doing hot swap at all when these have gone to solid state? And this is, I think, the final straw, that there's no expensive server. There's no reason to swap it out. So you would just add in another sled of OFP capacity. It's so dense and power conserving and doesn't take a lot of expensive server space. There's no reason to repair it, fix it. Just let it degrade and lose a little bit of capacity over time.
It's interesting. I've been in the industry long enough to, like a lot of the things that we've done as an industry as stopgaps to scale infrastructure are we're coming full circle where some of those aren't needed anymore. And the innovation that is occurring, NVMe over Fabric was something of a stopgap, putting servers in and tying them into storage systems together so you can have scale out shared data was, really something of a stopgap. But now there's a driving factor with AI for substantially more efficient. Otherwise, AI won't realize its capabilities and its promise. So this is really urgent now.
The way I think about it is, 15 years ago when Fusion IO pioneered high-performance flash, enterprise-grade high-performance flash, flash became the performance tier. But we still had disk drives for the capacity tier. AI, with its constraints on power budgets and Moore's Law and the improved density and lower cost of the NAND flash, have now made it possible for flash to have a much lower TCO than even hard drives and a way lower power consumption. And it can keep all of your data at an ultra-high parallel file system performance level the entire time. So now flash is becoming the capacity tier. And if you think about it, Fusion IO, its main innovation, the aha moment for me when I founded the company was, we're being stupid by putting flash behind RAID controllers and SATA and SAS buses and talking those protocols, or even worse, behind a storage network in a SAN. We should put the flash upstream of all of that directly on the server's arteries, disintermediating all of those trappings which limit flash from shining at what it does. Now what I'm proposing is that for the capacity tier, we take a further step. We step over the very server itself and go directly to the NIC and the network and disintermediate all of that power consumption and commensurate space consumption and, frankly, performance degradation and put flash upstream, disintermediating the server itself. And that allows this to shine as the capacity tier and be much higher density. So it's the same thing of disintermediating the trappings of the old world. Storage buses, controllers, protocols, storage servers, etc., and even abandoning the trappings of hot swappability as a useful concept. It's not compared to the amount of density that you get with flash. Mm-hmm.
So there's a lot of benefits. And when you think about who will be able to, take advantage of this kind of platform, we've talked about some of the big cloud companies or, some of the big AI institutes. Is that really who OFP is targeted towards? Or do you expect that these kinds of efficiencies will be driven into enterprise data centers?
The hyperscalers and neoclouds are great because they're very high volume. And that is what it may take to get OFP to become a commodity readily available. But I believe the true impact comes in the enterprise space because the enterprise doesn't have time for complex systems, bulky and power consuming, don't have time to build new data centers or worry about that. They need to be able to fit in their existing data centers with their existing power budgets and with a complexity that that they can manage because they don't always have access to the top talent that have been gravitated to the hyperscalers. So I believe enterprise is what's truly transformed when we can fit an exabyte where it used to fit a petabyte. And that has to happen ultimately because of, again, geometric growth in our data demands. And if you think about it, the absence of this kind of thing is kind of why enterprise has relegated the responsibility of this to the clouds because of perception that to get to exabyte scale, I gotta lease it from somebody else who knows how to own and operate it. But if you've suddenly brought down the complexity, space, power, everything needed, cost to run an exabyte because it fits in a rack, for goodness sake, why would you necessarily think of doing that on a leased basis of using cloud infrastructure in the first place. Especially when you're having to now bolt these things up to GPUs and feed the data, and where data is the critical asset with AI. So people aren't really going to want to put their data on other people's services or other people's infrastructure. It's a lot of sovereign cloud, private cloud kind of models for this. So that's where I think the real value comes in of making, exabyte into the new petabyte is just what the implications are for complexity, for owning and operating things at that scale.
Sounds like a really great initiative. I know there's a site, openflashplatform.org, where folks can stay up to date on developments. And also, I think that you'll be demonstrating a prototype at the Open Compute Project, or OCP Summit, here in a couple of months as well. Maybe just talk a little bit about how this maybe will tie to OCP and why we would consider that you would want to put a prototype there.
OCP is all about the commoditization of hyperscale infrastructure. And while we have helped with OFP initiative, it's our expectation that ultimately this becomes an OCP spec. That's where we believe this goes. But we wanted to solicit our industry partners and others to take multiple steps. If you can think about it, it's kind of 3 steps. The industry's trying to move to higher density SSDs with QLC and ultimately with nearline flash. But the move to DPUs away from separate servers, and the move towards using the depth of the rack and consolidating by having the power hold up at the DPU level and the hot swappability at the DPU level instead of the individual flash devices. So, these innovations are kind of like moving 2 more steps into the future beyond where we currently are with just trying to get higher density SSD devices. We want to pioneer the way. And the reason why you're seeing such an energy around this from Hammerspace is because it allows flash systems and parallel file system architectures that's standards-based, where the entire data path is nothing but native Linux. It allows that to truly shine and commoditize an open architecture instead of these closed architecture that require a wall of controller servers and where you're having to build all of these new functions on the other side of the wall. This allows you to have an open architecture with such high performance that that you can build everything in a standards-based fashion. You can embrace existing storage system. You can embrace commodity Linux, and you can embrace commodity Linux embedded in the DPU.
Awesome. Well, thank you for joining the show today and walking us through some of the details of the initiative. Maybe towards the end of the year, when you're getting closer to seeing some of the product in the market, we'll have you join back and talk a little bit more about what type of users are adopting it initially.
You bet. Looking forward to that, Molly. Thanks,
David.
Thanks for having me on the show.
Thanks for listening to Data Unchained, powered by Hammerspace. To learn more, visit hammerspace.com. If you have a guest you would like to hear on the show, email me at molly@hammerspace.com.